We have discussed the RSA algorithm and we understood the ingredients of the algorithm, various steps involved in it. And finally, when once you finish the algorithm, you have the key pair, number one, and also you know how to encrypt and decrypt. We also understood that with the technique behind it is the strength of RSA is that on a conventional computer, that means on a digital computer, to execute or to find prime factors of a given large number. When I say large, it is of a magnitude of some hundreds in digits. For that number, how to find the prime factors? We don't have a algorithm. That's actually a problem. Based on that problem, your strength of RSA algorithm lies. Okay. So this is about the RSA algorithm. So if you look at the current RSA uses 2048 bit length. So just if you want to put the 2048 bit length in a decimal format, you see a number. This is one number. This is one number which is of 2048 bit. So you see that number, it's a huge number. So, but still what happen is, though there are no computationally feasible algorithms, but on a smaller bits, like say 256 bit, 512 bit, RSA was broken. Okay, RSA was broken. That's the reason why people are going for RSA of 1024, 2048 bit length. Now, this is what so far we discussed is RSA, which is which encryption algorithm? Which encryption algorithm RSA? Public key encryption algorithm. Next you have Diffie-Hellman key exchange algorithm, which is also a asymmetric key encryption algorithm, but I am not going to touch about the Diffie-Hellman key exchange algorithm, which again you can read. Again, if you observe the Diffie-Hellman key exchange algorithm, the strength of that particular Diffie-Hellman key exchange algorithm lies with the fact that you need to calculate discrete logarithm. Okay, what is the strength of RSA? Finding the prime factors of a number. Strength of Diffie-Hellman is calculating the discrete logarithm. Again, for that we do not have computationally feasible algorithms that would work on classical computers. Right? So, strength of Diffie-Hellman algorithm, which is a public key encryption algorithm, is lies with this non-availability of or non-solvability of which problem? Discrete logarithmic problem. So this is the algorithm about Diffie-Hellman. Of course, the purpose of Diffie-Hellman is to exchange the keys. Once the Alice and Bob execute the Diffie-Hellman, what they get is the common key. Okay? Common key, which is common key. Once common key is there, what encryption can be used? Symmetric encryption can be used. So Diffie-Hellman purpose is for that. Now we spoke about symmetric encryption algorithms. We spoke about asymmetric encryption algorithms. Next, we have keyless algorithms, which are hash functions, right? So what are the hash functions? The purpose of hash function is they take the message, apply the message over the hash function, you get a digest. So when I have the message, when I apply hash over it, what I get is hash value, or also I call it as digest, message digest. For what purpose I can use? I can see if the integrity of the message is there or not. How do I do that? For a given message, imagine my message is hello. Somebody has removed this E or somebody has removed O. What is lost? Integrity is lost. In order to check the integrity of the message is there or not, what I can do? I can apply hash over my message, create the digest, and at the receiver side, what the receiver would do? Receiver takes the message and digest, then calculate h of m, compare that with the digest. If both are same, That means integrity is there or not? Integrity is there. If not, integrity is lost. That is the main purpose of hash functions. Okay, there are certain properties of the hash functions. There are certain requirements for the hash functions, and there are various algorithms for the hash functions. Now, the popular one is the most predominantly used is secure hash algorithm, 512 digit algorithm, which is current standard in hash algorithms, right? Remember, most important thing is hash are one way. When I say one way, what do you mean by that? That means when I have the message, I can calculate digest. But if somebody gives you the digest and asks you to calculate the message, you cannot. So, given m, calculating h of m is possible. Given h of m, calculating message is not possible. That is the reason why you call it as one-way functions. Okay. Given the digest, you cannot calculate the message back. Now tell me, what is the difference this with the encryption? Encrypt and you can decrypt. Hashes, no decryption. That means you can't reverse back. That's why it is one-way functions. Okay, it's called one-way functions. And similarly, there are other properties like, when I create a digest for one message, I should not get the same digest for another message, right? When I have for one message, when I have a digest called m, when I have, say, I have an m, when I have m, I calculate h of m will be not equal to h of another message, should not be. So no two messages digest should be equal. Okay. So if it is equal, that means what will happen is there is a collision. There is a collision. But is it practically possible to create such digest? If you think, what is happening with hash function is you are taking a message. Message would be of finite length or infinite length. It can be of variable length. But when you create the digest is a fixed length. Right? Digest is a fixed length. So that means you are taking the larger space, mapping it to a smaller space. What is our requirement? Collision should not happen. But in a practical scenario, is that possible? That's not possible. Imagine I have, say, 20 people in this room. What is the chance that no two people have the same birthday? Two people having the same birthday? Same birthday. So today is June 23rd. Anybody has the same birthday of two people having the same birthday? There are chances, right? Since we have 20 people. There are chances, there are no chances at all. But there are chances that since 20 people are there, but there are 365 days in a calendar, it is chance that no one will have same day as a birthday, common date. But imagine you have 500 people in the room. Can I have two people having the same birthday? Yes, because I have more number of people. So when my message is of more number of digits and I am trying to bring it to fixed length, collisions do exist. But the point is that whether the collisions were found or not. Okay. So if you observe among the algorithms such as sharp-white-pearl, people could not find collisions. What is the heading here? Closely observe. Collisions there or not, it is not the point. Collisions found or not. Do you understand the difference? Do you understand the difference? See, it is like this. It is like this. There is a key in my pocket. Do you see that? No. So collisions are there, collisions would come, but question comes, if you identify the collision only, problem comes. So far people could not identify the collisions with the SHA fight one. Okay, so that's the point. Okay, so this is the algorithm. Again, I don't deal with this algorithm now. Another crypto primitive is message authentication codes. Okay, when you look at hash functions, what we did is we have taken h over m. This is my message, and I applied hash function over my message. Imagine if for my function I am taking message and key and creating hash of it, it is called MAC, message authentication code. So what is the difference between a hash code and a message authentication code? In message authentication code, you use key. Which key is used? It is symmetric key. Now if you observe, Alice is sending a message to Bob. Alice takes the message, takes the key, apply the hash, that means m over k, with the help of hash function, get MAC. Take this message and append the MAC code, send it to Bob. What Bob would do? Bob takes the message and the MAC code, again over that m, apply the hash code with the help of that key, get the MAC code, compare the MAC code, calculated MAC, received MAC. If both are same, integrity of the message is prevailing, otherwise it is lost. So hash based message authentication code comes into picture. You have a which key? Symmetric key. Symmetric key, right? What is that we achieved? Message authentication. Few slides back, I said about digital signatures, right? Digital signatures for authentication purpose. Now the question is, can I use MAC code for digital signature purpose? No. Reason is, both ends you are using the same key here, but in the signature you use different keys. Okay, so that is the difference you should understand. So now we spoke about symmetric, asymmetric, then we spoke about hash. Of course, I don't deal deeply with the hash algorithms. Similarly, we have message authentication codes. I didn't deal with the algorithms per se. You understand the concepts of it. Then once you know this, there are algorithms of symmetric, asymmetric. You have the challenge with regard to key management. What is the key management problem when I have a symmetric encryption? What is the challenge? How do I maintain keys so that I interact with everybody by keeping multiple keys? That is one challenge. Second challenge is, how do I distribute the key? Because you and myself are doing with the same key. How this common key gets established? That is the key management problem with symmetric key schemes. What is the key management problem with asymmetric key schemes? You are using my public key. You want to send a message, you want to send me a message, I am the receiver. What you are doing is, you are taking my public key. What is the key distribution problem there? The problem is, how do you know my public key? You may ask, sir, your public key it is public, everybody knows. Yes, it is not that just simply knowing, but knowing in a authenticated manner. How do you know that this is my public key? Otherwise, there is a chance for man-in-middle attack. Somebody can tamper, so she wants to know my public key. She is sitting in between, called man-in-middle, and she tampers that and she projects her key as my public key. You think that the key what you are using is my key. So how do you bring the authentication there? So in public key encryption schemes, authentication is the problem. So in the key management distribution, these are the challenges. Now the question is, so Alice, Bob, PUA, PRA, PUB, PRB. What is the question? How Bob knows? How Bob knows? What is the question? Public key of Alice. Is it that just simply knowing? No, in authenticated manner. In authenticated manner. What is meant by authenticated manner? How do you know that this is my public key? Sir, I know your public key, but I said if that is a simple scenario, you have man in middle attack. There are various schemes for having authenticated public key. What is that is used is digital certificate. What is discussed is digital signature. What we are talking is digital certificate. There is a difference. Signature is to authenticate the message. Certificate is to authenticate your public key. So, what is the certificate? Now, tell me, who gives you your graduated degree? University gives, right? You will get a certificate from whom? From university. That means there is a certificate authority which gives you certificate. Then what you will do, you take that certificate, go to an employer, show that look, I am a graduate holder. Then the interviewer will ask, who told you that you are a graduate holder? Who certified that? Look, there is a university certified this, and you show that certificate, right? Same concept. What I do is, Alice, Bob, go to certificate authority. Alice is going to certificate authority, giving public key of Alice. You see here, telling authority, hey, look, this is my public key. Can you certify this? So, certificate authority will give the certificate back. Similarly, you see here, Bob is giving his public key of Bob. Certificate authority is giving the certificate to Bob. What is that certificate contains? Certificate is an encrypted document. You see here, certificate is an encrypted document. How it is encrypted? It is encrypted with the help of private key of authority. When it is encrypted with the private key of authority, how you decrypt it? Public key of authority, right? So, if you notice here, the message is encrypted with the help of private key of authority. It contains timestamp, it contains the ID of A, and then public key. Can anybody tamper this? Can anybody tamper that certificate? In order to tamper certificate, what you need? In order to break the certificate, what you need? You need public key, right? You need a public key. But can you create the certificate? Because you need private key of authority. So, once Alice gets the certificate, Alice will tell the Bob, look, you want my public key, right? Take my certificate. So, Alice gives the certificate to Bob. What Bob can do? Taking certificate, what Bob can do? Bob can decrypt or not? Bob decrypt CA with public key of certificate authority. So, when Bob decrypts that certificate with the public key of certificate authority, what Bob understands? Bob understands that this certificate is issued by certificate authority, because that's why I am able to decrypt it with the help of public key of certificate authority. Once he decrypts, what he get? What is there in that? What is there in that? Number one, timestamp. At what time this particular certificate is issued, to whom it is issued, that is identifier of A, and also public key of A. Now, public key of A is known to the Bob in an authenticated manner with the help of certificate. Who issued the certificate is certificate authority, right? Digital signature is different, digital certificate is different. Digital signature, what you do? Take the message, sign it with the help of signer private key. Digital certificate is issued by certificate authority. Hope you are able to follow the difference. This is about signatures, right? I'm not going to deal much about it. So look at the signature. Alice took her private key, use signature algorithm, and on the message she signed. Okay. Once she signs the message, what she is doing is she is performing encryption. Encryption with the help of Bob's public key. Who is the Bob? Receiver. Receiver's public key will give you, receiver's public key and encryption will give you confidentiality. Signing with the help of sender's private key gives you signature. So signature document with confidentiality is sent. So now here it is decrypted and here it is signature verified. How signature is verified? With the help of signer's public key, Alice public key. This is digital signature. What we spoke about is digital certificate earlier. This is digital certificate. Certificate, you will get it for the purpose of showing to someone what is your public key. You will sign the document to ensure that the content of the message is intact and you are authenticating it. That is the difference. Okay. Is that clear? There are so many algorithms for that. I am not going to deal with that. So if you see here, signature algorithms are RSA based signature algorithms. What is RSA? Which encryption? Public key encryption. Why we are discussing this is that these are all under threat. Okay. Elliptic curve and all that. In addition to that, there are standard algorithms called digital signature algorithm, exclusive digital signature algorithm. Now, so far what we discussed is all about cryptography. We understood symmetric, asymmetric, hashes, MACs, digital signatures, digital certificates, and what are all the encryption primitives, variables that are there, and algorithms, what is the strength of RSA and all that. Now let us talk about quantum computing, right? So what is quantum computing and how it is going to pose challenge? So if you observe so far, whatever the public key encryption algorithms, they are all based on number theory problems. If you look at RSA, what is the strength of RSA? Strength of RSA is lies with the fact that we are unable to find the prime factors of a large number. Strength of a Diffie-Hellman algorithm lies with the fact that you don't have the algorithm to calculate the discrete logarithm. These are all the number theory problems. So your security of that algorithms is lies with that. But what happens is Peter Shor had shown that quantum computers can use the laws of quantum physics. What are all our computers? They use Newtonian physics. Quantum computers use quantum physics phenomena. Okay. So we'll see. I'm just going to talk about what is classical computer. Classical computer speed, you can increase by making the operations faster, in the sense either by increasing the clock frequency or by increasing the number of operations completed during each clock cycle. That is how you can increase the speed of the current systems. But quantum computers speed up not based on this particular phenomena, but based on the quantum physics phenomena. We will understand what is quantum physics. But before that, you understand in our classical computers, information is stored in the form of bits, right? 1, 0. In the case of quantum computer, you call them as qubits. Okay? A bit and a qubit. So if you observe the quantum computers and classical computers, one difference is that the bit in the classical computer and qubit in quantum computer. We will see what is qubit. And before that, classical computers are deterministic in nature. Okay, they are all deterministic in nature. Quantum computers are probabilistic in nature. In the sense, you write an algorithm, a program for an algorithm, you run that particular program. When you run the program with the same input, will you get different output every time? I repeat, you have a program, you run the program with the same input 5 times. Each time you get a different output. Such systems are deterministic systems where when you run n number of times the same program with the same input, you get same output. Probabilistic computers are when you run that algorithm, the program with same input, you get different outputs at different instances. So quantum computers are not deterministic. The output is probabilistic in nature. Okay. So I'll just you have the best example is to understand the qubit notion is. So look at this coin. I know there is a lot of concept behind it, and I'll just try to simplify it because we need to delve into the other. So what is this is a coin, right? You have a head, you have a tail. There are only 2 states, 0, 1, like your bit, head and tail. At any point of time, I'm going to keep it here. At any point of time, if you ask, it will be either head or tail. That's all. That is the bit. That is the classical bit. What happens in the case of qubit is physically implemented. There are technologies like ion traps, etc., adiabatic simulated annealing. There are various physical models in a way that your qubit, it will be like this. When you toss it, now see here, it revolves. Now when it is revolving, somebody asks you, what is the state of it? No. At any point of time when you observe, your qubit would be in both states, head state, tail state, 1 state, 0 state. Classical bit will be always in either this or this, whereas a quantum qubit will be in both states. But now you want, sir, no sir, how, if it is in both states, I want to measure it. I want to measure it. When you want to measure it, it should settle down, then you have to measure it. You can't measure it when it is in the quantum state. When it is in the quantum state, it is in the both states. That is called superposition state because it is in the 2 states. Okay, that's what is superposition. Bit has 2 possibilities, 0, 1. So it is in both states now. Qubit is in both states. Whereas a bit either would be with 0 or with 1, head or tail. Whereas a quantum, it would be always in, okay, either both 1 and 0. This is with 1 qubit. It is in superposition state of both 1 and 0, rotating between 1 and 0 very fast, spinning between both states, oscillating between both states in a very fast manner. Right? That is called superposition state. This is with 1 qubit. Right? Now, with quantum physics, you can also achieve that. I am showing you how 1 bit only, right? 1 qubit. Is it that you will have only 1 qubit? You can have multiple qubits. Like this, you can have multiple qubits. So this is one. Imagine I have one more coin, one more coin, one more. So you have multiple qubits. All qubits are in superposition states. That is one thing. Second thing is, these qubits can also be in entanglement state. What does it mean? This qubit is linked with this qubit, and all these qubits can be linked together. What is that? Qubits can be linked together. Okay? You understand? So that means when you are trying to measure the system, one qubit is influencing another qubit. Okay? These are all not independent bits like in our classical computer. In quantum, bits, qubits are linked together, interconnected together. What is that phenomenon called? They are entangled. Okay? So when they are entangled, remember they are working. So one qubit is in the superposition state, another qubit is in the superposition state, and they are working together. Okay? So they are entangled. There is another word called measurement. What is measurement? When qubits are in the superposition state, quantum state. No, suppose if I say that, look, this is the qubit and it is in the quantum state. Okay? It is in the quantum state. That means it's keep on in the quantum state, you will not. So at a point you need to know the answer, right? So you expect that I want to measure it. When you are measuring it, the quantum phenomenon is getting collapsed, okay, to the measurement. That means, they get, if you want to measure it, it should not be in the superposition state, it should be in the normal state. It should come, okay. So when it is in the superposition state, as I said, you have both 1 and 0. And is it only one qubit? No, you have multiple qubits working together. So entanglement, then there are some definitions such as coherence, interference, all that I am not going to discuss them. You can see that. I'll show you one example. So imagine you have 2 qubits. Okay, so imagine you have 2 bits. What are the possibilities? You say 0, 0, 0, 1, 1, 0, 1, 1. You create the logical gates out of these 2 bits, right? You have AND gate, you have OR gate and all that. So if you are using a quantum computer, all 4 possibilities can be encoded into the state of 2 qubits via superposition. Okay, so the 2 qubit system requiring, so you have a single quantum gate with this all 4 combinations that would operate on all 4 states in parallel. That is what is the beauty of quantum computer. So that means, imagine you have 2 qubits, possibilities are 0, 0, 1, 0, 0, 1, 1, 1. You can see the quantum system with 2 qubits would be there at a time with all 4 basic states. A classical computer, either it would be 0, 0, or 1, 0, or 1, 1, or 0, 1, any one. Whereas in the case of quantum, you can have with the 2 qubits all 4 possible states at a single instance. Okay. So instead of one state, all 4 possible states at a one instance. That is where your massive parallelism is coming from quantum computers. Okay. So because of that only you have the benefits of quantum computer. One is the superposed states and being probabilistic in nature. Then you have entanglement, wave particle duality. It is like this. There is lot of theory behind it, there is lot of physics behind it. You can see excellent literature. Even people correlate that our human mind is also a quantum system. See, take an example, you have multiple things that are running, right? At a point of time, if a question is asked, you see that if there is no question, you are listening, you will feel about the what I am talking about. You will think about something else which you may have to travel back. Something about your classes at your institute, all those things, right? Now imagine there is a query, all those thoughts gets wiped out. You will keep thinking about the answer, what you need to answer, right? So there is a lot of interesting literature about bringing this quantum phenomena to the cognition, bringing this quantum phenomenon of multiple states being together, which is a superposed states, number one. Number two, qubits connected together in the form of entanglement, all that. But bringing this is theory. Realizing that a qubit, such that qubit is in the superposition state. How do you physically build such computer? You understand? Sorry. How do you build a computer such that your qubit is getting rotated like this, spinning like this, and above that, even if you physically do that, you have to write an algorithm using or exploiting that particular superposed qubits to work for your problem. So one side hardware, another side software. That means writing the algorithms for it. So both are side by side happening. So if you look at the quantum computing work, number one, physical realization of quantum computers, that means by building qubits, number one. Number two, when you are having qubits, what I said is you have a bit getting rotated like this, number one. It cannot just like that rotate, right? It should use that energy. And this bit is also interacting with the another qubit, right? Getting entangled. All this should happen in a noise-free environment. Okay? But it's in a practical scenario, so it's not so. All that leads to the noise. So how do I minimize the noise and make quantum computers? So whatever the people today are claiming, whether it is Google, whether it is the AWS or whatever, whoever is claiming the quantum computers, they are all, it's not that they are noise free. Okay, there is a noise. They are trying to mitigate that particular noise. Okay, they are all noisy quantum environments or quantum computers. So this is a table where you can get it from this particular article, which is comparing the classical computers and quantum computers in terms of the way information gets stored, the way information is processed. Bit is fundamental block, but from bit what you need is gate, but from gates you need to have registers and all that, right? So similar to your quantum regular gates, you have quantum logical gates. Okay, the gates that exhibit the quantum behavior, you have the gates. Okay, similarly, when you observe the mathematical operations, we use Boolean algebra operations, whereas in the case of quantum computer, we use complex linear algebra operations. Okay, there are certain advantages, there are certain disadvantages with classical and as well as quantum. Somebody says that quantum computers are going to come, what she is using her laptop, can that be a quantum computer? Absolutely not. You need to have a classical computer. You cannot just like that say that I'm going to use a laptop which is a quantum computer. It's not possible. Even in the future, you have a classical computer in place and also you will have a quantum computer in place. The point is that why you use a quantum computer? You should use a quantum computer for the problems which are not tractable by the classical computers, right? But when you use that quantum computers, obviously the threats also comes. Okay, so what are the threats? The threats is AES, symmetric key encryption, right? With Current, if you use 128, no, you cannot. So you should go for larger key size. Your RSA algorithm, your digital signature standards, elliptic curve algorithms, Diffie-Hellman key exchange algorithms, they are all no longer secure. Okay. Why they are no longer secure? That's the question. Okay. The question is why they are no longer secure. Now tell me, what is the problem on which uh, uh, RSA is secure? Yes. Based on the problem that you don't have the algorithm, to calculate prime factors of the large number. But you have an algorithm called Shor algorithm. Okay, you have an algorithm called Shor algorithm that gets executed on classical computer plus quantum computer. That means this algorithm has steps that gets executed on the quantum computer. Okay, if they are executed on the quantum computer, you can break RSA algorithm. Okay, so what is that? In order to implement Shor algorithm, what Shor algorithm is doing is, Shor algorithm is not directly taking the problem as finding the prime factors of the large number. Instead of that, it is taking that problem into a different problem. Okay, instead of taking this problem of finding the prime factors to a different problem. What is that different problem? The problem is called period finding problem. Okay, what is actually Shor algorithm is doing? Shor algorithm is trying to find period, or you call it as a period finding problem. What is period finding problem? Is that you have to find a number which is a period. Okay, you have to find a number called period such that f of x plus period is equal to f of x. Okay, for a given function, if you have that period, f of x plus period is equal to f of x. That is called period finding problem. Let us see what is that. So it is this. I have a function. What is that function? A power x mod n. Okay, I have a function called f of x called, where my f of x is defined as a power x mod n. And for this function, my aim is to find a period called R, such that what will happen? F of a comma n of x plus R is equal to f of a comma n of x. I need to find an integer called R such that my f of x plus R is equal to f of x. If I am able to find that R, I can calculate the prime factors. What is that prime factors? Here if you notice, my n is large number, okay, for which I am actually trying to find prime factors. Okay, so if you see here, n is the large number for which I am trying to find the prime factors. A is any randomly chosen number, and what is my function? A power x mod n. And for that particular function, what I am trying to find? An integer called R. That R I am calling it as period. So R is period. Such that f of x plus R for the numbers n and a, what is that I am supposed to get? F of x. If I am able to find that R, I will be able to calculate, if I get factors of n. I will be able to find it. So let us see how it is happening. Okay. So for that purpose, I'll give you the algorithm. We'll work out. So now imagine my first step is the SHAR algorithm goes like this. The first, what is the number? I have the number n to be factored. In the sense I need to find the prime factors. So this is how it goes. Okay. So first step is the n. Then I'm going to choose a random number between 1 to n and call it as k. Okay. I'm choosing a random number between 1 to n and I'm calling it as k. Then calculate GCD of n comma k. Okay, greatest common divisor of n comma k. Then if GCD of n comma k is not equal to 1, then k is factor of n. If GCD of n comma k is equal to 1, then go to step 4. Okay. So imagine if your condition of GCD of n comma k is not 1 is satisfied, your k is the factor of n, then you go back to step 2 and choose a different k. So next what you do is you find smallest positive integer r such that f of x is equal to k power x mod n f of a is equal to f of a plus r for any a. So you are going to calculate an r. Now what is this r? Is the period. Okay, such that for that particular function f of x, you take any a, f of a is equal to f of a plus r. Okay. So how do you find this r? Take a new variable called q and assign q is equal to 1. .2 step is find q into k mod n. Okay. If remainder is equal to 1, then go to step 4.3. If not, set q value as remainder. So what we do is we took a new variable called q and q is equal to 1. we found q into k mod n. If the remainder value is 1, then we go to the next step. If the remainder value is not 1, what we do is we assign that remainder value to the q and repeat it. That means we iterate it. Okay. So also we find how many iterations we are doing. Okay. So 4.3 step. The number of repetitions we made in 4.2 is R. Okay. The number of repetitions we made in 4.2 is R. Okay. The fifth step is if R is odd number, then go to step 2 and choose a k value, new. Otherwise, go to step 6. In step 6, what we do is define a variable p, which is the remainder value in r by 2th repetition. If p plus 1 is equal to n, then go to step 2 and choose new k. The last step is factors of n are f1 is equal to GCD of p plus 1 comma n, f2 is equal to GCD of p minus 1 comma n. Okay. So this is the algorithm called Shar algorithm. Okay. I repeat, look at the first step. N is the number for which you are trying to find the factors. For that purpose, the second step, you have chosen a random number called k, which is between 1 to n. Then you calculated the GCD. If GCD is not equal to 1, then your k is the factor of n. Go to step 2, find a new k. If GCD is 1, then you are going to step 4. What is the 4? Here you are trying to find the smallest positive integer r, which is the period. How do you do that? You take a new variable called q and assign it to 1. 1 into k, q into k mod n you are calculating. If remainder value is 1, then you go to the 4.3 step. If not, what you do? You got some remainder value, right? That remainder value you are assigning it to q. Again you repeat, which is that q into k mod n. How many times you need to repeat? Till you get remainder value as 1. You are tracking the number of repetitions. That number of repetitions form your period. That is that r value. Okay. Are you going to stop with that? No. If r is odd number, then we go to the step 2. and choose a new k value. Otherwise, what we do is we are defining a new variable called p. And what is that p? How many iterations we made is the r. R by tooth repetition remainder value. Please listen carefully. What is that? Number of repetitions made are r. Number of repetitions by 2. Imagine I have made 6 repetitions. My third repetition, whatever is the remainder value, that I am assigning it to p. Okay. Imagine I have made r number of iterations. R by tooth iteration remainder value I am assigning it to p. Imagine if p plus 1 value is n, again I am going back to step 2. If not, my factors are GCD of p plus 1 comma n is my first factor, GCD of p minus 1 comma n are my second factor. This is the Shor algorithm. In this algorithm, if you observe, what happens is steps 1, 2, 3, 5, 6, 7 are all executed on classical computer. Okay? Steps 1, 2, 3, 5, 6, 7 are executed on a classical computer. The fourth step gets executed on the quantum computer. Okay? The period finding gets executed on the quantum computer. So, remember, number 1, if you have a quantum computer right now, what you can do is execute that fourth step on the quantum computer. Rest are all executes on classical computer. Gets that quantum computer output and find 5th step, 6th step, 7th step and find the factors. If you have the factors, calculate number 1, are there prime factors? I am not saying they are prime factors. You need to check if they are prime factors or not. If not, you repeat it. The point is that on a classical computer, 4th step cannot be done. Okay? 4th step cannot be done. But on a quantum computer, 4th step can be done easily and hence you can find the factors. And once you find the factors, what happens is, once you find the factors, you can find prime factors and then break the RSA algorithm. Okay. Now, how it is done is that number 1, as I said, in quantum computer, you need to have quantum qubits and quantum gates. Once you have the quantum gates, the period finding can be done with the help of quantum Fourier transformation. You know Fourier transformation? Quantum Fourier transformation, with that help, people can find the period. You can try this example. It is this. I don't deal this one. So take an example. I'll just give you quickly. Imagine n is equal to 15. N is equal to 15. My k value I have chosen is 7. Okay. K value I have chosen is 7. What we are doing is actually f of your, what is the, this one is f of n comma k over 0. If you take, I am doing k power x mod n, right? K power x mod n. So 7 power 0 mod n. What is the value? 1. Similarly, you take f of n comma k 1, you get 7 power 1 mod n. What you get? what you get is 7. So f of n comma k with 2 is 7 square mod n. What is n is 15. You get 4. Then 7 cube mod n, which is you get 13. 7 power 4 mod n, which you get 1. What is that you got? You got 1 get repeated, right? So every 4 repetitions you get 1. So R value is, I'm just giving you R value is 4. R value is 4. The period value is 4. Now, what is the P value? P value is R by 2th repetition. R by 2th repetition remainder value. So that means 4 is my P value. Okay. So I don't take this one. So 1, 2, 3, 4. So my R value is 4. It so happened here that your remainder value is also 4. This is number of steps, repetitions. This is the remainder value. Okay. You understand? So even you can try the numbers maybe later. You can see if you take these numbers, n is equal to 357, k is equal to 205. You will see all combinations that are discussed in the algorithm. What are all the combinations? Number 1, choosing a k value, GCD of n comma k value. If it is not equal to 1, then that k value is the factor. So in this case, you will find that conditions getting satisfied. So you have to choose a different k value, which is, I think the example that I have noted is k is equal to 52. If you take that k value, then you will see the steps goes. Okay. So try, you will be able to understand the algorithm per se. But now the point is, the whole algorithm, is it that the whole algorithm goes for the quantum? No, only that particular period finding value. The reason is that because you are exploring, it is simple, you are exploring, here how many possibilities you got is 4. With qubits in a superposition state and entangled, you can find all these combinations at a time. That's the huge advantage of quantum computer. Otherwise, what you are doing, you are going one by one, right? In quantum, all these things can be executed at a time because you have a qubit that are entangled. All qubits can work at a time in parallel and explore the whole huge large space. See, we have taken only 2-digit numbers. What is that actual scenario we are exploring? Digits of 100 in nature, 100 digits number. This is only 2-digit number, right? What we are talking about is 100-digit number, 200-digit number. Then you can think of possibilities that you can get. And all these possibilities at a time they get explored. So massively you can solve it. So only that particular step goes to the quantum, not the remaining steps. Once you find R, again you come to 5, 6, 7 at classical computer. So how do you achieve this? Getting this whole space into the quantum is through quantum Fourier transform. This is the logical architecture to implement the Shor algorithm. So this is possible if you have, number 1, again, what is that current available quantum computers? They are all NISQ quantum computers. What is meant by NISQ? Noisy intermediate state quantum computers. If you have access to even these noisy intermediate state quantum computers, they are with 50 to 100 qubits, not more than that. But if you really want to actually break an RSA algorithm with 1024 bit, 2048 bit, you need an actual quantum computer. Is it that readily available? No, it may take another decade, or in the sense by 2030. But the point is that if we sit till 2030 expecting that realization of a quantum computer and we try to build the models, it won't work, right? So, next, what is the other algorithm we have is the Grover algorithm. I am not going to discuss the Grover algorithm, but I will tell the what is the Grover algorithm. So, Grover algorithm is mainly meant for search algorithm. Okay, it is mainly meant for search algorithm. If you look at the symmetric encryption algorithms, what is the symmetric encryption algorithm like DES and AES? They operate by sharing the keys. How do you break that if you know the key? How do you know the key? So obviously you need to do a brute force. So that means what is the possible key space? Whatever the possible key space, if you explore all possible keys, that is brute force search. If you use Grover's algorithm, imagine you have a telephone catalog, which is an unsorted catalog having n number of entities. Typically, if you are searching for a number in a telephone directory which is unsorted, which takes n searches, on average n by 2 searches on an unsorted telephone directory. Whereas if you apply Grover algorithm, you can minimize it to root n steps, which is significant in comes to the algorithms such as AES. You can break the symmetric encryption algorithm by performing brute force search over symmetric encryption algorithms key space. So that means I have a AES algorithm, 128 bit algorithm. What are all possible keys? 2 power 128 possible keys. I search. Okay, what is my this one? If you see, I am going only to perform 2 power 64 operations. Whereas in the case of a classical this thing, I have to perform 2 power 127. Half of things gets reduced with the Grover algorithm. I'm not going to deal with that algorithm, but you can understand the gravity of it. So what obviously you can do is, instead of making 128, make it to 256. Okay, so you are actually trying to make this particular set of operations also more. That's how you can escape the threat of quantum computer in symmetric encryption algorithms. But you don't have such flexibility when it comes to asymmetric encryption algorithms. Okay. So that is about Grover algorithm. This one. Okay. So when it comes to quantum, as I said, you have PQC, which is post-quantum cryptography algorithms, then quantum cryptography algorithms. I will go to the post-quantum cryptography algorithms right now. I will quickly give a perspective of post-quantum cryptography algorithms. So now people said, sir, I have Shor algorithm which is going to break my public key schemes. What is the current techniques that are there in quantum crypto algorithms or post-quantum crypto algorithms? So in the very beginning I said, what are the post-quantum crypto algorithms? They are meant for mitigating the threats from quantum computer. What is the threat from quantum computer we have seen is the Shor algorithm. So how do you mitigate it? The mitigation strategies, there are 4 strategies. One is hash-based signatures. Have we discussed hashes or not? We discussed hashes, right? Hash functions. So hash-based signature algorithms is one approach using which we can mitigate the problems that are arising from quantum computer. That is one set of techniques. You say whether hash-based signature is an algorithm? No. There are multiple algorithms. Okay, Merkle tree based algorithm, Lamport algorithm, like that. There are algorithms under hash based signatures. Similarly, Multivariate cryptography is another branch of post-quantum cryptography, wherein which you have various other algorithms. When I say algorithms, it's not that they are standard. Okay, people are proposing. You look at NIST website. NIST is calling for post-quantum crypto algorithms. NIST is asking for post-quantum crypto algorithms. They are asking, when I say asking, you can also propose an algorithm. Like that, throughout the world, people are proposing the algorithm. NIST is testing them, posing that algorithms to the outside world. People are trying to break them. Right? Once it is thoroughly tested only, that comes as a standard, right? So they are under the process. Multivariate cryptography, code-based cryptography, lattice-based cryptography. These are all various branches under post-quantum cryptography, and again, under all of these branches, you have separate algorithms. Okay, you have separate algorithms. Have you discussed? Has the blockchain concept is discussed in this one? What is the data structure used for blockchain? Huh? Linked list. Okay. There is one more tree structure. What is the tree structure? In block. Okay. Merkle tree. Merkle tree. Merkle tree is discussed, right? So the same Merkle tree comes in your hash-based signatures. So I'll just quickly go to that particular tree structure. I will skip all these algorithms. I'll go to the hash-based. So this is Merkle tree. What happens in the Merkle tree is the leaf nodes are the data elements. So you see here data 1, data 2, data 3, data 4 like this. So you are creating hash of data 1, right? Then this is hash of data 2. What is this? Hash of data 3. This is data 4. What you do here is hash of hash 3, hash 4, right? And this is hash 1, 2. This is Merkle tree, right? So this is the root hash. What happens in your blockchain? The leaf nodes are your transactions, right? So transaction 1, transaction 2, transaction 3, transaction 4. You create hash of each transaction. Root hash would be stored in the block, and that blocks gets interconnected. And since you are recording the root hash in the block, you are calling that chain is immutable, because if anybody changes the transaction, what happens? Your hash values changes. So that is not possible, and hence you call it as immutable. Same philosophy here. Hash-based cryptography is used for signature purpose, because signatures are supposed to be not tampered, right? Signature should not be tampered. Similarly, the way you are creating the blocks with non-tamperable transactions, hash-based cryptography uses signatures which are not tamperable and verifiable. Okay. So this is called inclusion proof in the hash-based cryptography, in the sense, I want to know whether a particular data item or a transaction is included in the tree structure or not. How do I verify? See, look at this example. Data item 1, 2, 3. You can think as transaction 1, transaction 2, transaction 3. What is A? What is A? What is A? Yes, hash of 1, right? This is B is hash of 2. Then this is hash of 3, right? So then what actually we are trying to do is, we are trying to find whether 2 is there in the tree or not. How we are checking is, I am giving, this is the root hash. This is the root hash. So what I announce is, the root hash I will announce. I will announce root hash, which is E. I will announce 2. I will announce record 2. What I am announcing? I am announcing root hash and I am announcing record 2. My objective is to say whether record 2 is included in my tree structure or not. What I have given? Root hash I have given. I have given record 2. I am asking you to find whether record 2 is there in the tree structure or not. How do you check? Is this way. That is called inclusion proof. How do you check? Okay, you gave me record 2. What I will do is, I will calculate hash of record 2. What is hash of record 2? What is hash of record 2? So from record 2, I will calculate B. Okay, I will calculate B. After calculating B, I will ask, can you give A? Okay, remember, I am not asking you 1. I am not asking 1. I am asking A. What is A? I am asking you hash of 1. Okay. So once I have B, I will ask you A. If you give me A, that means what you are giving is transaction hash. You are not giving the transaction. Remember, if you give me hash, can I calculate that message? No, right? It's one way. So I take only A. Once I have A and B, can I calculate C or not? I can calculate C. I can calculate C. Then I will ask you to give D. I am not asking you 3. I am asking you the D. Once I have C and D, I can calculate E or not. When I calculate E, what I will check? The E whatever you have given. This is called inclusion proof. Any doubts? This is called inclusion proof. Okay. Remember, what is the objective? Objective is to know whether a record is there in the tree structure or not. The objective is to record is there in the tree structure or not. Record can be a record can be a signature, record can be a transaction, record can be a public key. So now here, the hash based cryptography, the root is the root hash, the leaf nodes are public keys. Okay, public keys. I keep my symmetric keys with me. I don't reveal public keys just like that. I will reveal only the root hash and I will reveal only my public key. Now I am not getting digital certificate. Instead of digital certificate, what I am giving you is root hash. I am giving you public key. Now you want to know whether my public key is correct or not. How do? You go with this. So this is, so because of that, your signature problem can be managed with the help of hash based cryptography, right? And before we conclude, whatever we spoke here is, number 1, there are threats from quantum computer towards cryptographic problems. That is about PQC. Okay, we spoke about PQC. Now what we are talking is about quantum cryptography. What is quantum cryptography? I said in the beginning, how do you use quantum principles? What are the quantum principles? Number one, qubits, and qubits, quantum gates, quantum registers, etc., and all that. Along with that, I have quantum principles such as superposition, entanglement, etc. How do I use them for building security solutions? How do I use them to build security solutions? What are the security solutions? Number one, either I try to get confidentiality, integrity, authentication. On top of that, you have one fundamental problem why we are going for asymmetric key schemes. What is that fundamental problem asymmetric key schemes are solving? Key management, right? What is that key management? When two people like Alice and Bob wants to interact, they wanted to have a symmetric key. So for that purpose, we went to a symmetric key scheme, and asymmetric key schemes are now having the threat from quantum. Imagine if that key distribution problem, if I am solving with the help of quantum computers, I need not go for asymmetric scheme, right? So I am going to address key distribution problem. So the question is how I am going to distribute the keys. When I say key, symmetric keys, so it is like this. So both Alice and Bob wants to have a common key. So how the common key gets established between Alice and Bob using quantum principles. That is called quantum key distribution. If I use quantum key distribution, which key I am establishing? Symmetric key. Once you have symmetric key, what algorithms you can use? AES, etc. Right? Okay. Before we go to this one, you need to understand that we are going to exploit the quantum principles such as quantum superposition, entanglement. I have shown you superposition, right? A bit, qubit in a state of both 0 and 1, and one qubit is interacting or entangled with another qubit, right? This is how it goes. Alice wants to send Bob and establish the quantum key. Now here there are two channels. So far we are talking about one unsecured channel, which is already there. This is unsecured channel, public channel. On top of that, there is another channel called quantum channel. Okay. In this quantum channel, what happens? Alice is going to send the Bob, what he is going to send is qubits. Okay. This particular key, whatever this key is encoded as qubits. How these qubits are encoded again in the quantum computer is through photons. What is a photon? It is, you can think it as a light ray, okay, light of particles, okay, a light source, a wave of particles of light. So it is like this. So imagine that I am just putting a torch like this. Okay. So see here, there is a light gets, right? When this light goes, it's not that this light is going like this. What this Alice did, Alice is going to use different polarizations. Okay, there is a concept called different polarizations. So he is going to put a filter called a horizontal vertical filter to that light. So that filter looks like this. horizontal and as well as vertical filter. There is one more filter or basis called diagonal basis. So he puts filter, horizontal vertical filter or diagonal filter. You understand? First I am sending 1 qubit. So the light goes, put horizontal vertical filter, first qubit. Second qubit changes my this filter. Third qubit, I am just changing it randomly. The Alice is going to change this randomly. Okay. So this is how it goes. Okay. So you have horizontal, vertical, you call it as a polarization, okay, or a basis, or also you can call it as rectilinear basis, or else you can call diagonal basis. You can have the light goes through this particular basis. In this particular way, I can transmit 0 or 1, right? So when the Alice is using, this is Alice and Bob. When Alice is wants to send 1, he can send 1 either using horizontal vertical basis or diagonal basis. Similarly, Alice can send 0 either using horizontal vertical, that means rectilinear, or diagonal. Which one she chooses is her choice. Now the light goes. When the light goes, when Bob receives, Bob has to capture it. At that time, Bob also will use his own basis. When he is using a basis, it could be again a rectilinear basis or diagonal basis. Again, he uses randomly. It's not that since Alice has sent horizontal vertical basis, Bob is going to use same horizontal vertical basis. He may use that because you don't know what the basis Alice has used. Okay, Alice is using randomly basis, Bob is also using randomly basis. Now you see this. Okay, this is Alice and this is Bob. Okay, Alice is sending the bits 0, 0, 1, 0, 1, 0, 1, 0, 1. This is the bits. Look how she is sending. To send 0, what she used? Diagonal or horizontal, rectilinear? Diagonal basis she has used. So she's transmitted the light in this particular polarization state. Okay, as a diagonally, because 0. So see 0 diagonally. So when you see the diagonally, you see that it is 45-degree angle. Okay, 45-degree angle of diagonal, she is sending the light using the diagonal basis. What Bob did? What is the basis Bob has used? Vertical or horizontal, that means rectilinear basis. Obviously, will he be able to measure as same? No, because the basis is different. So he measured it as horizontal. What he got is 1. What he got is 1. Then don't come to this. Don't come to this now. Next, 0 she is sending. When she is sending 0, what she is using the basis? Rectilinear. And polarization angle, your 90 degrees angle. What Bob did? Same basis he has used, and hence he got same polarization angle, and the bit would be 0. You understand? Are you able to follow? Like this for all bits. Let us take last bit. 1. What is the basis? Rectilinear basis. Horizontal polarization angle, which is 0 degree. 0 degree horizontal what? Binary 1. Bob is using what basis? Rectilinear. What is that result he receives? 0 degree horizontal Obviously, what is the bit he measures? 1. Done. Now, Alice has sent, Bob has measured. Now, point is, so far, Alice has sent, Bob has received. Now, the question comes probing. Alice will not tell what is the bit she has sent. Bob will not tell what is the bit he received. Alice will tell only the basis. Bob also will tell the basis. Basis they have used. So, in this case, Alice says, look, I used diagonal basis. Bob says, I used rectilinear. Gone out. Okay? Similarly, Alice says, I used rectilinear. Bob rectilinear. Matches? Yes. So, I take that bit as output 0. Like this, you see wherever that matches, only those bits would be considered 0, 0, 1, 0, 1. Like this, you transmit the entire key to the receiver and you probe. Once you probe, wherever the basis matches, only those bits would be considered, rest of the bits would be discarded. So, those bits that are considered would form the, what is this key? Symmetry. A key got exchanged. Have we used public key encryption? No. So, without using public key encryption, what is that we have used is quantum principles of transmitting light. So, there are a couple of questions would arise. Number 1, imagine if any attacker sits in between, captures the light, what will happen is your quantum phenomenon gets collapsed and hence, you will not have light getting received at the receiver side, errors gets introduced and hence, you will know that yes, there is an interceptor. It is not that attacker cannot be removed here. Attack can be happened. Advantage is that you will know that there is an attack. If you know that there is an attack, what you can do? You can discard that entire key. That's the advantage of quantum key distribution. Is it complete foolproof? Absolutely not. There are chances that this would actually, even if the bases are same, bits measurement may vary. See here, look this example. What is the polarization used? Diagonal. What is that is sent is 1. What is measured is 0. What is measured is 0. So, even if your basis is same, there are errors comes into this particular concept because of your errors in the measurement. Even this has to be handled. Okay, how they would be handled? Whatever the example we have seen is the sequence of maybe around 10 to 15 bits. Generally, it would not be. There would be large number of bits gets transmitted. Then randomly, some bits would be verified. Only those bits cannot be again considered for the key. They would be discarded. So random sampling would be taken. In that sampling, they will check if there are any errors. Okay, so that's what is mentioned here. If you see here, there may be even if the transmission basis and measuring basis match, bit errors do occur. So there are possibilities. So it's not that the protocol is foolproof or error-free. Still, it is getting evolved. So this is called BB84 protocol. That means this protocol is proposed when 1984. Okay, so there are different versions and all that. So point is that we are trying to manage what we are trying to manage. Which problem? Key distribution problem. Once we do that, key gets established. Okay. So if you look at the short term is people are working on post-quantum cryptography algorithms, hash-based cryptography, code-based cryptography. These are all the 4 different variations I have said, algorithms for that. Then on the long term, about quantum cryptography, which includes your QKD. Okay. So this is what is expected down the line, which is taken from the Accenture white paper on the quantum cryptography. Okay. So there are various literature that is available, especially I would suggest you to check NIST standards, because NIST is trying to come out with the algorithms, and whatever the algorithms, current algorithms, they are under the experiment mode. It is not that they are standardized. So tomorrow somebody, even if they announce the algorithm, tomorrow they may be seeing that algorithm is broken. So there are no such standards. People are trying to evolve. Even the companies like Accenture, Boston, many companies, IBM, they're all working on the algorithms. Those who are really interested, only thing is that you need to know the fundamentals of cryptography and quantum principles. When I say quantum principles, understanding them is little dry, but of course, even if you are as a computer science student, you don't deal directly with the hardware, right? So physical aspects of hardware, that's okay, even if you don't understand. But you should understand the software aspects of it. When you understand the software aspect of it, somehow, there are libraries now, Python libraries and all that people are using. That if you look at what is important is that we have seen that step by step of Shor algorithm. When you do that step by step of Shor algorithm, you are actually going to the core logic of it. When you know core logic of it, you can write the program. When you know the core logic of it, you can write program it using either Python or any language, right? So with that, I would like to conclude. If you have any queries, questions, I'll be able to answer. So as I said, if you look at the algorithm what we discussed is the Shor algorithm, right? We look at the algorithm, we have written the algorithm. So if you notice this algorithm, what is that we said? You have about 7 steps in the algorithm. What we discussed in the 7 steps is where your quantum computer is needed, only at that 4th step. You don't require quantum computer from 1, 2, 3, you don't require 5, 6, 7. Only for 4th step you need quantum computer. So it is this, when you have a problem, you need to check whether that problem needs that computing. The reason is that you are taking not just program, you are taking the data to the quantum computer. You need to convert from classical to quantum. When quantum gets executed from 4.3, again you are coming to classical. So this is the conventional. So in a sense, you are going in a hybrid manner, classical, quantum, classical. Now I have a problem where it is purely to be executed over quantum, right? Obviously, we need to write a pure quantum algorithm. The best example is QKD. No classical phenomenon. Only thing is that only at the end you are announcing the bits. You say that yes, not bits but the bases. That's all. Right? So it's all about the problem. And now the point is the many of these especially some of the companies like IBM, they have come out with their own software libraries, and they are providing access to their computers of quantum, which you can connect via cloud and then use them, play with them. They are giving the sample codes, you can play with them. Okay. IBM Quiz-Kit. No, madam, you can access via online. IBM Quiz-Kit. UISKIT. Okay. Yes. They have given the programs. simple programs which you can run via cloud and see. No, madam. IoT. That's what I just said. This is, even that if the fourth step cannot be managed in a classical. So we went for that. Fourth step cannot be managed for cloud. For classical, we went for that. So it is all about what is the problem. If the problem demands such huge computing, massive parallel computing power, then if problem don't demand, it is of no use. And even classical is better. Classical is better. Yes.